In this chapter, we'll introduce foundation models and how they power modern AI applications. You'll learn core concepts, common use cases, and what skills and tools you need to start building with these models. One word captures modern AI: scale. The largest models, ChatGPT, Gemini, Midjourney, are so massive they use a non-trivial share of global electricity and are consuming huge amounts of web data, raising sustainability concerns and the risk of running out of publicly available training data. As AI models grow, they gain new capabilities and can solve a wider set of problems. That makes AI useful to more people and teams who apply it to raise productivity, generate economic value, and improve everyday life. The net effect is wider adoption and larger real-world impact. Training large language models requires huge datasets, massive compute, and specialized engineering. Resources only a few organizations can afford. To make these capabilities widely usable, those organizations expose their models as a service, typically via APIs, allowing developers to build AI applications without the upfront cost of training their own models. Demand for AI applications is rising at the same time that models and tooling have become much easier to use. That combination lowers the barrier to building AI products and has turned AI engineering, the practice of building applications on top of ready-made models, into one of the fastest-growing engineering disciplines. Building applications on top of machine learning isn't new. Recommender systems, fraud detection, and churn models have powered products for years. The core principles of putting ML into production still matter, but large, general-purpose models change what's possible and introduce new operational and design challenges. This book focuses on those new opportunities and the problems teams must solve. We'll begin with foundation models, the core technology that triggered the recent boom in AI engineering. Next, I'll show a range of real-world use cases to highlight where AI performs well and where it still struggles. Although capability growth makes precise forecasting hard, recognizable application patterns help us find immediate opportunities and hint at plausible future directions. We'll close by summarizing the new AI stack. What changed with foundation models, what stayed the same, and how the AI engineer's job differs from a traditional ML engineer's. Foundation models move focus away from training every model from scratch toward model selection, prompting, and system-level integration, while core engineering practices, data quality, evaluation, and reliable pipelines remain essential. The AI engineer adds responsibilities for integration, safety, and product behavior. We'll introduce why AI engineering has emerged as its own field, driven by scale, safety, and the complexity of deployed ML systems. Expect a brief overview of the roles, skills, and practices that distinguish AI engineering from traditional software or research work. Foundation models grew out of earlier language models, a lineage that stretches back to the 1950s. While tools like ChatGPT and Copilot feel new, they're the result of decades of incremental advances. In this section, we'll trace the key breakthroughs that turned simple language prediction into modern AI engineering. In this section, we'll trace how standard language models grew into what we now call large language models. I'll highlight what large means in practice and why increasing scale changed their capabilities. A language model is a system that learns to predict text and judge which word sequences are likely. The recent ability to scale these models comes from self-supervision, training on large amounts of raw text by predicting missing or next tokens, so no manual labels are needed. If those ideas are familiar, feel free to skip ahead. We'll introduce what a language model is and why predicting next words is fundamentally a probabilistic task. You'll learn the core idea. Models assign probabilities to sequences and the common forms they take in NLP. A language model captures statistical patterns of a language and uses them to score how likely different words are in a given context. So for the prompt, my favorite color is underscore underscore underscore. The model will usually give a much higher probability to blue than to car because of English usage statistics. In the 1905 story, The Adventure of the Dancing Man, Holmes noticed the most frequent stick figure and inferred it represented the most common English letter, E. This is an early example of frequency analysis. Languages have predictable statistical patterns that help decode encrypted or unknown text. Claude Shannon applied statistical methods during World War II to help decipher enemy messages. In his 1951 paper, Prediction and Entropy of Printed English, he introduced ideas like entropy and probabilistic prediction that still underpin modern language modeling. Early language models were built to handle one language at a time. Today's models are trained on multilingual data or architected to process many languages, allowing them to share representations across languages and serve users worldwide. A token is the basic unit a language model processes. It could be a single character, a whole word, or a subword piece like tie-in. For example, GPT-4 breaks, "I can't wait to build AI applications," into 9 tokens. Note that the contraction can't becomes 2 tokens, can NT. You can experiment with different tokenizations on the OpenAI tokenizer page to see how models split text. This close-up of a sign highlights texture, lighting, and any visible lettering. Look for the typography and surface where to infer purpose and age. Notice how contrast and composition direct your attention to the most important elements. This figure shows how GPT-4 breaks a short phrase into individual tokens. We'll examine the token boundaries and note how common words, punctuation, and subwords are represented. Tokenization is breaking text into the model's basic units, called tokens. For GPT-4, an average token is about 3/4 of an English word, so 100 tokens is roughly 75 words. A helpful rule of thumb when estimating prompt or reply length. The model vocabulary is the set of discrete tokens the model can work with, like a compact alphabet used to build words and text. Tokenization method and vocabulary size are design choices by the model developers. Larger vocabularies can represent more distinct units directly, while smaller ones combine pieces to form words. Quick note: this section highlights an important point to keep in mind as we proceed. Pay attention now so you can apply it correctly in next steps. Tokens are a middle ground. They're smaller than whole words, but larger than single characters, so models keep sequence lengths manageable while still representing meaningful subword structure. Using tokenization, BP/word piece, lets us have a fixed size vocabulary, avoid out-of-vocabulary words, and make training and generation much more efficient. Begin by listing everything the problem gives you: variables, numerical values, and any diagrams or constraints. Writing these down first makes it easier to choose the right method and avoid mistakes later. Models work with tokens, which can be whole words or smaller subword pieces. By breaking cooking into cook and ing, the model preserves root meaning and recognizes the grammatical endings separately, which helps with understanding and generalization. Begin by reading the whole problem and identifying exactly what is given and what's being asked. Noting constraints and key quantities up front prevents mistakes later and guides your solution strategy. Tokenizers break words into subword pieces, so there are fewer distinct tokens than distinct full words. That reduces the size of embedding and output layers, which lowers memory use and speeds up computation. See the efficiency discussion in Chapter 2. This label marks the first item wheel address. I'll explain the intent and steps for this part, then solve it step by step so the result is clear. Tokens let the model split unfamiliar words into meaningful pieces so it can infer structure and meaning. For example, the made-up word chatting can be tokenized as chat plus ing, preserving the root and the suffix. This gives a compact representation with more semantic content than raw characters while using fewer units than whole word tokens. Language models come in two main families. Masked models, e.g., BERT, predict masked tokens using both left and right context, while autoregressive models, e.g., GPT, predict the next token using only previous tokens, and that difference affects their strengths for understanding versus generation. A masked language model is trained to predict tokens that have been replaced by a mask, using the surrounding words as context. This forces the model to learn bidirectional, contextual representations, as in BERT, that transfer well to many downstream tasks. A masked language model learns to fill in blanks anywhere in a sequence by using context from both before and after the missing token. For example, given my favorite underscore underscore is blue, it should infer color. BERT is a well-known model trained with this masked prediction objective. Masked language models are commonly applied to non-generative tasks like sentiment analysis and text classification because they learn bidirectional context. That same bidirectional understanding makes them useful for context-heavy problems, such as code debugging, where a model must consider both the code before and after a line to detect errors. An autoregressive language model predicts each token by conditioning on all previous tokens, so generation proceeds left to right. It factorizes the joint probability into a product of next token conditional probabilities and produces text by sampling one token at a time. An autoregressive language model is trained to predict the next token in a sequence using only the tokens that come before it. For example, filling in the blank in my favorite color is underscore underscore. Because the model generates one token at a time, it can continue sampling token after token to produce long passages, which is why autoregressive models are the common choice for text generation compared with masked models. Figure 1. Two contrasts two broad categories. Autoregressive models that generate text by predicting the next token left or right, and bidirectional or masked models that use context from both sides to fill in or score tokens. Keep this distinction in mind. It explains key differences in training objectives and what each model can do. This is a crossword diagram with a chicken-themed puzzle. Notice the grid layout and where answers intersect. Those shared letters are the constraints that let you deduce entries from overlapping clues. This figure contrasts two common model families: autoregressive models, which predict the next token sequentially, and masked language models, which predict missing tokens from a partially hidden input. We'll refer to this distinction when we discuss generation versus bidirectional context. This is a brief note to highlight an important assumption that affects the upcoming examples. Keep it in mind because it changes how we interpret results and apply the methods that follow. Throughout this book, the unqualified term language model refers to an autoregressive model. That means the model generates each token by conditioning on the tokens that came before. If we mean a different setup, we'll state it explicitly. A language model has a fixed, finite vocabulary, but can combine those tokens in countless ways, so its possible outputs are effectively infinite. A model that can produce such open-ended text is called a generative model. hence the term generative AI. A language model treats the prompt as the beginning of a sequence and predicts what comes next, one token at a time. It selects continuations that are statistically likely given its training data. So its job is to produce plausible completions rather than to reason like a human. We'll look at a simple example next to make this concrete. This is a prompt completion pair. The prompt is to be or not to be, and the model's completion is that is the question. When you concatenate them, you get the famous line, to be or not to be. That is the question. Note how the completion begins with a comma and a space. Leading punctuation and white space in a completion determine the exact final text, so preserve them when demonstrating or constructing prompts. Language model completions are generated from probability estimates, so they can sound plausible even when incorrect. This probabilistic behavior makes models powerful and flexible, but also a source of surprising errors. We'll explore this trade-off in Chapter 2. Completion means predicting how a prompt should continue. Many tasks, like translating a sentence, summarizing text, writing code, or solving math, can be written as completion problems. For example, completing "How are you" in French is to comment CAVA performs a translation. We'll look at a concrete prompt next and use it to demonstrate how to analyze intent and produce a clear response. Pay attention to the key constraints and the expected output format as we walk through it. This line is a prompt asking you to judge whether a given email is spam. The placeholder, email content, is where the full message appears, and answer is where you would state your verdict. When evaluating, scan the message for classic spam signals: unexpected sender, urgent request for money or credentials, suspicious links or attachments, poor grammar, and mismatched headers, and weigh those signals together to decide likely spam or not. When a language model fills a prompt with the phrase, likely spam, that single completion is effectively a classification label. This illustrates how model outputs can change how we interpret the system. The same underlying LM can act like a classifier depending on the prompt and completion. A completion model predicts likely next text, but that doesn't guarantee a helpful reply. If you ask a question, it might simply append another question or continue the prompt instead of answering. The post-training section shows how to shape model behavior so it responds appropriately to user requests. Now we'll introduce self-supervision, a family of methods that derive training signals from the data itself instead of using external labels. We'll outline the core ideas and why they produce useful representations. Language models use a single, dense objective, next token prediction, so they learn from huge amounts of diverse text and get strong supervision at every token. Combined with the transformer architecture and vast compute/data, this produced general capabilities that emerge with scale and can be steered by prompting or fine-tuning, making LLMs unusually adaptable and widely useful. Supervised learning trains models on labeled examples, which are costly and slow to produce. Self-supervision creates training signals from raw data itself. For example, predicting masked words, so models can learn from vastly larger unlabeled datasets and overcome the labeling bottleneck to scale up. In supervised learning, we give the model examples paired with the correct label and train it to reproduce those labels. For example, you can train a fraud detector by supplying transactions labeled fraud or not fraud. Once trained, the model can predict whether new transactions are likely fraudulent. The deep learning breakthrough of the 2010s relied heavily on supervised learning. AlexNet was trained on ImageNet, a dataset of over 1 million labeled images, and learned to assign each image to one of 1,000 categories, for example, car, balloon, monkey. That scale of labeled data and supervision drove the major gains in visual recognition. Supervised learning depends on human-labeled data, and those labels become expensive at scale. At 5 cents per image, labeling a million images costs about $50,000, and requiring 2 independent labelers per image doubles that bill. If you try to cover a million different object categories, the labeling expense alone rises into the tens of millions of dollars, creating a serious scalability and budget challenge. Some labeling is cheap and easy. For example, Tagging everyday objects needs little training. Other tasks demand specialists or extra effort. Producing accurate Latin translations for a model costs more. And medical labels, like determining whether a CT scan shows cancer, require expert clinicians and are therefore very expensive. Self-supervision removes the need for manual labels by deriving targets directly from raw data. In language modeling, each sequence supplies both contexts and the next token labels the model must predict. For example, the sentence, "I love street food," can be turned into several next token training pairs. 6 samples in Table 1.1. This table shows how a language model is trained. Each row is a context next token, training pair extracted from the sentence, "I love street food." The context starts with a special BOS token and grows one token at a time. The target is the very next token. The model learns to predict that next token at every step, continuing until the special EOS token marks the end. The special tokens BOS and EOS mark the start and end of sequence, so a model can handle multiple sequences reliably. Each marker is treated as one special token by the model, and the end of sequence token is especially important because it tells the model when to stop generating. A quick note before we proceed. This clarifies an important assumption that affects the upcoming examples and ensures you interpret results correctly. Self-supervised learning construct training targets from the input itself, for example, predicting mass tokens or transformations, so labels are inferred from the data. Unsupervised learning, by contrast, does not use labels at all and instead discovers structure like clusters or density. The key distinction is whether you generate labels from inputs, self-supervised, or work entirely without labels, unsupervised. Self-supervised learning means models learn from the structure already present in text, so we don't need human labels. Because written text is everywhere, books, articles, blogs, forums, researchers can assemble massive training corpora that let models scale up into large language models. There's no fixed cutoff for calling a model large. What counts as large shifts as models and hardware improve. We typically use the number of parameters, the trainable variables, to measure size, and Generally, more parameters mean greater capacity to learn complex behaviors. When GPT first appeared in 2018, 117 million parameters was considered large. A year later, GPT-2 pushed that to 1.5 billion, and today models around 100 billion parameters are described as large. This illustrates how our definition of large shifts as model scale advances. Larger models have greater representational capacity, so to fully use their parameters, you need proportionally more diverse training examples. Training a huge model on a small dataset usually wastes compute. It tends to memorize or overfit, and a much smaller model would often match or exceed its performance at far lower cost. In this section, we'll trace how the focus shifted from large language models to the broader category called foundation models. We'll highlight what this conceptual change means: training on broad data, producing versatile representations, and serving as a base for many downstream tasks. Large language models can perform impressive text-based tasks, but they only work with language. Humans perceive the world through vision, hearing, touch, and more. So AI must process non-text data to operate effectively in real environments. Researchers are extending language models to handle more data types so they can solve richer tasks. For example, GPT-4V and Claude 3 understand images, and other models can process video, 3D assets, and even protein structures. OpenAI described adding modalities as a major frontier because it meaningfully expands what models can understand and do. Models like Gemini and GPT-4V are often called LLMs, but the term foundation models is more precise. It emphasizes their central role in AI and that they're designed as reusable bases you can build specialized tools and applications on. Historically, AI research was split by modality. NLP handled text, computer vision handled images, and audio models handled speech. Each modality had its own tasks: translation and spam detection for text, object detection and classification for images, and STT/TDS for audio. Foundation models are a breakthrough that blur these boundaries and enable unified, cross-modal systems. A model that works with more than one data type, text, images, audio, is called a multimodal model. When it's a generative model that predicts the next token from those multiple modality tokens, we often call it a large multimodal model, or LLM. This contrasts with a text-only language model, which conditions its next token prediction only on text tokens. A multimodal model conditions on text plus image or other tokens. Focus on the overall structure. Inputs enter on the left, move through the central processing blocks, and emerge as outputs on the right. Notice the arrows that show data flow and any feedback loops that indicate where the model is updated or trained. This figure illustrates how a multimodal model predicts the next token by combining signals from both text and visual tokens. We'll look at how information from images and words jointly influences the model's prediction. Multimodal models also scale with self-supervision. OpenAI used natural language supervision. They scraped co-occurring image, text pairs from a web to build about 400 million examples, roughly 400 times ImageNet, avoiding manual labels and enabling Clip to generalize across many image classification tasks without extra training. A brief note highlighting an important caveat you'll need for the upcoming steps. Pay attention. It clarifies assumptions and common pitfalls that could affect results. We use the term foundation models as an umbrella label that covers both large language models and large multimodal models. In other words, any large pre-trained model that handles text alone or text combined with other modalities falls under this term. Clip wasn't trained to generate open-ended outputs. Instead, it maps images and text into a shared embedding space. Think of embeddings as vectors that capture the semantic meaning of the original data. These multimodal embeddings are commonly used as the backbone inside generative systems like Flamingo, LLVA, and Gemini. In the past, we built models for one task at a time. A sentiment model wouldn't help with translation, and vice versa. Foundation models are trained at scale, so a single core model can be adapted to many different tasks instead of being limited to one narrow use. Foundation models are trained at large scale and can perform many tasks out of the box. For example, An LLM can handle sentiment analysis and translation without extra setup. When you need higher accuracy for one particular task, you can tweak the model, for example via fine-tuning, prompt design, or adapters, to maximize its performance. Figure 1.4 summarizes the tasks used in the supernatural instructions benchmark to evaluate foundation models. The set includes classification, generation, extraction, and other task families, giving a quick sense of the range of behaviors these models are measured on. A generic text model can produce accurate product descriptions, but it often won't capture a retailer's unique brand voice or messaging. Those outputs tend to read like boilerplate marketing, full of cliches, and may not highlight what makes the product special. We'll need targeted customization and constraints so descriptions align with the brand's tone and priorities. Notice the different colored circles and how they're positioned relative to one another. Pay attention to clusters, overlaps, and spacing. These visual cues suggest groups, relationships, or emphasis the diagram is conveying. This figure summarizes the range of tasks included in the supernatural instructions benchmark. We'll refer to it to see how the dataset spans different task types and formats. You can shape model outputs in three practical ways. Prompt engineering uses detailed instructions and examples. Retrieval augmented generation, RAG, lets the model pull in external data like customer reviews, and fine-tuning further trains the model on a curated set of high-quality product descriptions. There are three common techniques for adapting a model to your needs: prompt engineering, retrieval augmented generation, RAG, and fine-tuning. Prompt engineering sculpts behavior by changing inputs. RAG augments responses with external documents at inference time. Fine-tuning changes the model's weights for a persistent behavioral shift. The rest of the book will walk through each approach, when to use it, and how to apply it. Adapting a foundation model to your task typically requires far less data and time than building a model from scratch. Sometimes 10 examples in a weekend versus a million examples in many months. Exactly how much data you need depends on the adaptation technique, and we'll cover that for each method in the book. Still, task-specific models can be advantageous. They're often much smaller, faster, and cheaper to run. Teams must decide whether to build a custom model or leverage an existing one. Balance practical trade-offs, development time, cost, control, and expected performance, and use the book's discussions to guide which option fits your project's constraints. In this section, we'll connect large, pre-trained foundation models to practical AI engineering, the steps for turning models into reliable, deployable systems. We'll outline the core skills, tool chains, and trade-offs you'll need to design, fine-tune, evaluate, and deploy real-world AI products. AI engineering means building applications that sit on top of large foundation models. It's distinct from traditional ML engineering or ML ops because these models change how systems are designed. They bring new capabilities, different integration patterns, and fresh operational and safety needs, which is why the label matters now. Traditional ML engineering focuses on developing models from the ground up. AI engineering instead composes and integrates powerful pre-trained foundation models, and the widespread availability of those models produces three complementary factors that together enable rapid growth in the field. This factor captures how well an AI performs across many different tasks, for example, reasoning, coding, language understanding, and multimodal perception. High general-purpose capability means the system adapts to new problems with little task-specific tuning, and therefore tends to have the biggest practical impact. These models do more than improve existing tasks. They enable entirely new kinds of tasks and products, including ones we hadn't thought possible. As capabilities unlock more useful applications across daily life, both the number of users and the demand for AI grow rapidly. Modern AI can match or exceed human writing and now automates, or helps automate, almost any task that involves communication. People use it to draft emails, answer customers, create marketing images and videos, and even synthesize training data or write code that fuels better models. Companies and governments are pouring more money into AI, funding research, buying cloud compute and specialized chips, and integrating models into products. That rising investment speeds up development, expands real-world deployment, and creates strong economic momentum behind AI-driven change. The success of ChatGPT sparked a big uptick in venture and enterprise funding for AI. Cheaper development and faster product cycles made AI investments more attractive, so companies raced to add AI. For example, Scribd's Matt Ross reported about a 100 times drop in estimated AI costs for his use cases from April 2022 to April 2023. Goldman Sachs projected AI investment could reach about $100 billion in the US and $200 billion worldwide by 2025, highlighting the scale of the economic opportunity. Firms increasingly call AI a competitive advantage. FactSet reported that in Q2 2023, 1 in 3 S&P 500 companies mentioned AI on earnings calls, roughly 3 times the rate from a year earlier. Figure 1.5 visualizes the steady rise in S&P 500 AI mentions from 2018 through 2023. This is a multi-line graph with numeric axes. Look first at the scales and tick marks to understand magnitude. Then track each line. Note whether it rises, falls, or crosses another line. Those intersections often mark important thresholds or trade-offs. This figure shows the count of S&P 500 firms that referenced AI during earnings calls, which peaked in 2023. We'll use this to discuss how corporate attention to AI surged and what it might signal about technology adoption. Wall Street then reports that companies mentioning AI in their earnings call saw an average stock increase of 4.6% versus 2.4% for those that didn't. This is an interesting pattern, but it doesn't prove causation. It may be that AI drives results, or that already successful, tech-forward companies simply talk about AI more. Pre-trained models, public APIs, open-source libraries, and managed cloud services remove much of the heavy lifting, so teams can prototype and deploy AI features without deep research or huge compute budgets. That accessibility lets many more developers turn ideas into working applications fast. Model as a service means providers host pre-trained models and expose them through APIs. Rather than running and serving a model yourself, you send a query to an endpoint and get back a response in a single call. This removes the hosting and serving burden and lets you integrate powerful AI into apps quickly. AI can write working code for you. So people without a software engineering background can turn ideas into prototypes and get them in front of users quickly. Many models also accept plain English prompts, letting you build and iterate without learning a full programming language. Training foundation models takes enormous compute, data, and engineering. So only major tech companies, some governments, and deep-pocketed startups can realistically develop them. For most developers and businesses, the practical opportunity is to customize and adapt these existing models for specific applications, a point Sam Altman emphasized. AI engineering has rapidly become one of the fastest-growing engineering disciplines. In just 2 years, open-source projects like AutoGPT, Stable Diffusion Web UI, LangChain, and Alma have collected more GitHub stars than Bitcoin and are poised to surpass popular web frameworks such as React and Vue. The chart, Figure 1.6, visualizes this unusually fast star growth for AI tools. In August 2023, LinkedIn data showed many professionals were adding tags like generative AI, ChatGPT, and prompt engineering to their profiles at roughly a 75% monthly growth rate. Computer World captured the trend by calling teaching AI to behave the fastest growing career skill. In other words, designing prompts and guiding model behavior is becoming a mainstream professional capability. This plot overlays several colored lines. Look at their slopes, where they cross, and how they separate over the x-axis. Intersections often mark important changes, and parallel or diverging segments show consistent differences between the series. This chart shows open-source AI engineering tools accumulating GitHub stars faster than other software tool categories. We'll use this as evidence that community adoption is driving rapid momentum in AI tooling. In this section, we'll unpack why the label AI engineering emerged and what it aims to describe. You'll learn how this role differs from traditional software engineering and from adjacent AI specialties. There are many overlapping labels: ML engineering, ML ops, LLM ops, but I picked AI engineering to emphasize the practical work of building reliable, scalable applications on foundation models. The term is broad and outcome-focused. It covers model, systems, and product concerns without fragmenting the discipline into tooling or model-specific buzzwords. The earlier section on AI engineering versus ML engineering shows that foundation models introduce different concerns than traditional ML systems. For that reason, I avoid using only the term ML engineering here. It doesn't capture those differences, yet ML engineering remains a helpful umbrella for shared processes. I avoided labels that end in ops because this material isn't mainly about running operational systems. It's about engineering foundation models, iteratively tweaking prompts, fine-tuning, and design choices to make the model do what you want. I surveyed 20 people building applications on top of foundation models to see what label they use for their work. The majority preferred the term AI engineering, so I chose to use the practitioner's preferred name. A rapidly growing community of AI engineers has produced a surprising variety of creative applications. In the next section, we'll examine the most common application patterns so you can recognize which pattern fits a problem and why it works. In this section, we'll survey practical applications of foundation models across industries. I'll highlight common patterns and concrete examples so you can see where these models add the most value. If you're not already building AI applications, recent advances make this an excellent moment to start. If you already have an idea, jump to planning AI applications. If you need inspiration, the next section surveys industry-proven and promising use cases across many sectors. Foundation models are highly flexible. The same base model can be adapted for translation, summarization, search, coding assistance, and many other tasks. Because they generalize so broadly, the set of practical applications is essentially unbounded and impossible to enumerate exhaustively. Different surveys sort enterprise generative AI use cases in different ways, so comparing studies can be misleading. For example, AWS groups cases into three buckets: customer experience, employee productivity, and process optimization, while a 2024 O'Reilly survey lists 8 categories, such as programming, data analysis, customer support, marketing and other copy, research, web design, and art. The takeaway: expect variation in labels and granularity across sources. Consultancies often group AI use cases by how they capture value. For example, cutting costs, improving process efficiency, driving growth, or accelerating innovation. Gartner adds a different lens called business continuity. For some organizations, adopting generative AI is seen as existential, and in a 2023 survey, 7% of 2,500 executives named business continuity as their reason. Allowed at all mark a task as exposed when AI can cut its completion time by at least 50%. An occupation's exposure is the share of its tasks meeting that cut. So 80% exposure means 80% of tasks are exposed. Their results show near 100% exposure for roles like interpreters/translators, tax preparers, web designers, and writers, while hands-on jobs such as cooks, stonemasons, and athletes show little or no exposure. This helps identify where AI is most useful today. This table reports occupations that human annotators judged to have the highest exposure to AI. Exposure can mean direct use of AI models or use of AI-powered software. The listed percentages show the share of workers in each occupation judged exposed, and several occupations were labeled 100% fully exposed. Here we have the sequence alpha, beta, zeta repeated twice. Alpha, beta, zeta, alpha, beta, zeta. Notice the repetition. This pattern can represent a periodic sequence or a repeating index set useful in examples of cycles and modular indexing. I examined enterprise and consumer uses separately. For enterprise, I interviewed 50 companies and read 100-plus case studies. For consumer, I analyzed 205 open-source AI projects with at least 500 GitHub stars. I grouped the results into 8 categories, Table 1, 3. This condensed list is a reference. Chapters 2 and 3 will give you the tools to build and evaluate foundation models, so you can decide which use cases fit. This table organizes common generative AI applications by category and contrasts how consumers and businesses use them. Consumers typically use AI for coding help, photo/video editing, writing emails and social posts, tutoring, chat companions, summarization, image search, and planning. Enterprises reuse those capabilities for presentation and ad generation, copywriting and reports, onboarding and training, customer support and product co-pilots, market research and knowledge management, and workflow/data extraction. Because foundation models are general purpose, apps built on them often handle very different tasks at once. For example, the same bot can provide companionship, aggregate information, extract structured data from a PDF, and answer questions about that document. So an app can belong to multiple categories simultaneously. This chart shows the distribution of use cases across the 205 open-source applications. The small slices for education, data organization, and writing don't mean those areas aren't popular. They're often delivered as closed-source or enterprise products, so builders targeting those use cases may prefer enterprise or proprietary models. This is a pie chart where each colored slice represents a category and its proportion of the whole. Notice the largest slice, any very small outliers, and whether colors cluster together. Use the legend or labels to map colors to specific categories. This figure visualizes how different use cases are represented among the 205 open-source GitHub repositories we analyzed. We'll use it to highlight the most common application areas and to identify gaps where fewer projects exist. A 2024 A16Z growth report found companies deploy internal-facing AI, like knowledge tools, faster than external-facing apps, like customer chatbots. Internal apps let teams build AI engineering skills while reducing risks around data privacy, compliance, and catastrophic failures. Also, although foundation models are general purpose, many production uses are closed-ended, for example, classification, which makes evaluation, and therefore risk estimation, much simpler. Look for the X and Y axes, the main trend line, and any peaks or annotations. These mark where the measured quantity changes most. Pay attention to axis labels and scale to interpret the magnitude and compare different regions of the plot. This figure shows that organizations generally prefer to roll out internal-facing applications first. In the next section, we'll examine the practical reasons: lower risk, simpler compliance, and clearer return on investment that make internal tools easier to deploy. Even after seeing hundreds of AI apps, new, surprising uses keep appearing. The field is still exploring itself. Think back. Few foresaw social media becoming the internet's main use. AI's eventual dominant application could be just as unexpected, and with luck it will be a positive surprise. In this section, we'll explore practical coding techniques and patterns you can apply right away. Expect clear examples and guidance to avoid common pitfalls when writing real code. Surveys repeatedly show coding as the most popular way people use generative AI. That happens for two reasons. Models are unusually good at programming tasks, and the early adopters and builders driving feedback tend to be software engineers who try these tools first. One of the earliest production wins for foundation models was GitHub Copilot. It reached over $100 million ARR within 2 years, showing code completion can scale commercially. Venture investors followed, with startups raising hundreds of millions, for example, Magic $320 million and Anysphere $60 million in August 2024, and open-source projects like GPT Engineer and Screenshot to Code each hit roughly 50,000 GitHub stars within a year, indicating rapid developer adoption. Beyond general-purpose editors and IDE features, many tools are built to solve particular development problems. Examples include testing frameworks, linters and formatters, profilers and performance tools, deployment and CI/CD helpers, and database migration managers. Choosing a specialized tool usually speeds work and improves reliability compared with a one-size-fits-all approach. This dash is a placeholder indicating a short pause or transition. There's no content here, so we'll treat it as an intentional break and move on to the next point. We'll use Agent GPT to automate extracting structured data from both HTML pages and PDF files. The agent combines web scraping, PDF parsing, and extraction rules to turn tables, forms, or key value pairs into clean, normalized datasets. This makes it easy to export the results for analysis, databases, or other automation steps. This paragraph summarizes the core idea and its significance, what the result is, why it holds, and when it applies. Focus on the single assumption that enables the conclusion and the main takeaway you should remember. These tools turn plain English questions into executable data code. DBGPT and SQL Chat generate SQL for databases, DBGPT as a general DB assistant, SQL Chat for conversational SQL, while Pandas AI produces Python/Pandas code to manipulate in-memory data frames. When you introduce a complex idea, put a short, clear summary on the slide, and then explain aloud. The on-screen phrase anchors attention, while your verbal explanation supplies the necessary detail and context. This task, often called screenshot to code, means taking a design or screenshot and producing HTML/CSS/JS that reproduces its layout and appearance. Projects like Draw UI automate parts of the process by detecting UI elements and mapping them to semantic code you can run in a browser. Keep the Canvas text short and focused. Aim for one clear idea per slide. Use your narration to add nuance, give a brief example, and connect this idea to what came before. Tools such as GPT-Migrate and AI Code Translator can automatically rewrite code from one language or framework to another, preserving core logic while adapting idioms, APIs, and project structure. Use them to accelerate migrations and prototyping, but always run your test suite and manually review platform-specific, performance-sensitive, and security-related code. This paragraph should state the main idea clearly and without jargon. Define any necessary term briefly. Give one short example or consequence, and end by connecting this point to the next step so the viewer understands why it matters. Autodoc automatically generates documentation from your code, extracting signatures, doc strings, and examples so docs stay current with the implementation. Use it to save time and produce consistent, readable documentation that reflects your code base. This paragraph is a placeholder. The input contained only a dash and no explanatory text. Replace it with the intended explanation or remove the block so the lesson flows correctly. We'll design tests that simulate real penetration test workflows using Pentaeus GPT. Define targets, goals, and expected outcomes so checks are automated, repeatable, and easy to audit. Check the project's GitHub for templates and examples. The source here shows only a dash, which serves as a placeholder for missing or intentionally omitted content. When you encounter this in a draft, either supply the missing detail or clearly mark the section for later revision so your audience isn't left wondering. AI can read code diffs and propose concise, descriptive commit messages. Tools like AI commits automate this step to improve consistency and save time during reviews. AI already performs many software engineering tasks, and some prominent leaders predict it could replace traditional coding roles. Others argue developers' work will shift rather than vanish. The key question is whether AI can automate the entire craft of software engineering, not just individual tasks. A lot of software engineers confidently assume AI won't replace their jobs. That confidence comes from technical arguments and from an understandable emotional reluctance to accept being replaceable. Together, these factors can blind people to real risks and make proactive planning less likely. Research summarized by McKinsey finds that AI can roughly double productivity for documentation and increase productivity by about 25 to 50% for code generation and refactoring. However, gains are minimal for highly complex engineering tasks, and many tool builders report AI is often stronger on front-end work than on back-end systems. Look at the vertical blue and white bars and compare their heights to read relative values. Pay attention to the tallest and shortest bars to understand the range, and scan for patterns or clusters where blue bars consistently exceed or fall below the white bars. Use those differences to infer which categories or time periods stand out. This figure summarizes McKinsey's finding that AI produces larger productivity gains on routine or simple developer tasks than on highly complex ones. We'll next examine why gains fall with complexity and what that means for choosing tools and structuring work. AI can make individual engineers much more productive, so companies may accomplish the same or more work with fewer people. That shift especially threatens outsourcing. Routine, non-core tasks are the easiest to automate, while strategic core work remains harder to replace. This section covers practical techniques for capturing, editing, and delivering high-quality images and video. We'll introduce common workflows, essential tools, and the quality checks professionals use. Because generative models sample from probable outputs, they're especially good at open-ended creative work. Companies like Midjourney, Adobe Firefly, Runway, Pika Labs and Sora turned that capability into fast growth. Midjourney reached about $200 million ARR within 18 months, and many top design apps now put AI in their names. This trend suggests AI will soon be built into graphics and design tools by default. Chapter 2 explains the probabilistic mechanics behind that. Using AI to create headshots is now common across platforms, and many job seekers use these images to put their best foot forward. Public perception shifted. In 2019, Facebook banned AI-generated profile photos for safety reasons, but by 2023, many social apps offer built-in AI tools for generating profile pictures. AI can generate promotional images and videos and help teams brainstorm or produce first drafts that human experts refine. It also creates many ad variants fast for A/B testing and can localize creative details. For example, changing leaf colors for fall or adding snow for winter, so you can see which versions perform best by audience, season, or location. This section covers writing, how to craft clear, effective prose, and practical steps to improve your drafts. We'll outline key techniques and short exercises you can use right away. AI has long been used to help with writing. Two familiar examples are your phone's autocorrect and autocomplete. Writing is a great fit for AI because we do it constantly. Many parts are repetitive or tedious, and small suggested errors are easy to ignore. If a suggestion isn't useful, you simply skip it. Researchers randomly assigned 453 college-educated professionals to complete occupation-specific writing tasks, giving half access to ChatGPT. Those with ChatGPT finished about 40% faster and produced writing rated 18% better. The model helped more for weaker writers, and participants were much more likely to adopt it in their real jobs in the weeks and months after the experiment. People use AI to improve everyday messages. You can turn an angry draft into a polite email or give a model bullet points and receive polished paragraphs. Many users now run important emails through AI before sending. AI is already being used to generate many kinds of books, from children's stories to fan fiction and romance. Unlike static books, AI can create branching, adaptive narratives so readers can shape the plot. For example, a kid's app can spot words a child struggles with and generate stories that practice those words. Many note-taking and email tools now embed AI that suggests edits, rewrites, and tone adjustments so you can write faster and with fewer mistakes. Grammarly takes this further by fine-tuning models on writing data, making its suggestions more fluent, coherent, and tailored to each user. AI writing can be used maliciously. The New York Times reported that Amazon was overwhelmed by low-quality, AI-generated travel guidebooks that included invented author bios, fabricated websites, and fake positive reviews, a clear example of how automation can be weaponized to game platforms and erode user trust. Companies commonly use AI to draft sales and marketing material and to speed internal communication. Managers increasingly lean on AI to help write performance reports, while teams use it for cold outreach emails, ad copy, and product descriptions. CRM platforms like HubSpot and Salesforce now include built-in generators to produce web content and outreach at scale. Many AI models learn SEO patterns from web text, so they can easily generate copy that ranks. Operators use this to run content farms, spinning up junk sites, publishing thousands of AI-written pages to attract ad traffic, and selling ad placements via exchanges. NewsGuard found hundreds of brand ads on such sites, and one site producing 1,200 articles a day. Without action, search results risk being dominated by low-quality AI content. In this section, we'll examine formal qualifications and practical learning pathways. You'll learn how to plan continuing education, compare degrees and certifications, and choose options that fit your goals. Students flood OpenAI's Discord whenever ChatGPT goes down, showing how reliant some are on it. Major districts like New York City and Los Angeles initially banned the tool to prevent cheating, then reversed those bans a few months later as they reassessed policies. Rather than banning AI, schools can use it to speed learning by summarizing textbooks and generating individualized lecture plans. AI can also adapt the format to each student. Read aloud for auditory learners, create interest-based visuals, or translate math into code, so students receive content in the style that helps them learn best. AI can role-play realistic conversations and practice scenarios, giving learners safe, on-demand speaking and comprehension practice. Research from Pajak and Bicknell, Duolingo, 2022, shows that, among stages of course creation, lesson personalization gains the most from AI, helping make activities more relevant and adaptive. This is a one-page white paper with prominent blue headings and clear margins. Notice how the blue-on-white contrast and the heading hierarchy make the document easy to scan, typical features of a concise professional summary. This figure shows how AI is used across each of Duolingo's 4 course creation stages and emphasizes that the biggest gains occur during personalization. We'll treat this as a roadmap and then dive into what personalization looks like in practice. AI can create and grade both multiple choice and open-ended quizzes, giving students fast feedback and saving teachers time. It also makes a strong debate partner by reliably presenting different viewpoints and is already used as teaching and course assistants, for example, at Khan Academy. Some teachers even assign AI-written essays for students to find and correct mistakes, an exercise in critical reading and editing. Many education companies adopt AI to improve products, but sometimes AI replaces their core offering. Chegg is a stark example. After ChatGPT launched, students increasingly turned to AI for homework help, and Chegg's share price dropped from about $28 to $2 in under 2 years. If AI can replace many skills, it can also teach them. Use AI to accelerate the early stages of learning, then apply deliberate practice and real-world experience to become better than the tool. In this section, we'll introduce conversational bots, what they are and why they're useful. You'll learn the core components, like language understanding and dialogue management, and the common design patterns used to build them. Conversational bots are very versatile. They fetch information, explain ideas, help you brainstorm, and can even offer companionship or therapy-like conversation. Lately, people have started using AI as digital girlfriends or boyfriends and sometimes spend more time with bots than with humans, which raises real concerns about how AI might change dating and relationships. Researchers have created groups of conversational agents that interact like members of a tiny society. This approach lets scientists run controlled experiments on social dynamics and emergent behaviors, as shown by Park et al. 2023. Customer support bots are the most common enterprise bots because they cut costs and improve experience by responding faster than human agents. AI can also act as product co-pilots that walk customers through difficult, error-prone tasks like filing insurance claims, doing taxes, or locating corporate policies. ChatGPT's success sparked many new text-based chatbots, but conversational interfaces aren't limited to text. Voice assistants like Google Assistant, Siri, and Alexa have been used for years, and 3D conversational bots are common in games and are now spreading into retail and marketing. Traditionally, NPCs are scripted with limited actions and preset dialogue, which makes them predictable. AI-powered 3D characters, shown in demos like Invidious and World and Convai, can reason, hold richer conversations, and adapt to player choices, changing gameplay in titles such as The Sims or Skyrim, and enabling entirely new kinds of games. In this section, we'll study how to combine individual reports or signals into a single collective estimate. You'll learn key aggregation methods, when they work, and common pitfalls to watch for. Keeping up with email, Slack, and news can quickly become overwhelming. Generative AI can aggregate those streams and produce concise summaries, so you can focus on decisions instead of data overload. Salesforce's 2023 snapshot found 74% of generative AI users use it to distill complex ideas and summarize information. AI lets consumers talk to their docs, upload contracts, disclosures, papers, or web pages, and query them in plain language. You can get concise summaries, extract specific facts, or compare multiple sources side by side. I used these tools while writing this book to quickly summarize and contrast research papers. Aggregating and distilling information efficiently cuts middle management overhead and helps teams stay lean. Instacart's fast breakdown prompt summarizes meetings, emails, and Slack into facts, open questions, and action items. Then those actions can be auto-inserted into project trackers and assigned to owners. AI helps you pull together the most important customer signals, demographics, needs, purchase behavior, and sentiment from CRMs, surveys, and social data, so patterns become clear. It can also automate competitor analysis, pricing, messaging, channels, and product gaps, so you can prioritize opportunities and threats quickly. When you collect more information, it becomes harder to use unless you structure it. Pair aggregation with clear organization, consistent names, folders or tags, and simple metadata, so data stays findable and reliable. In this section, we'll learn practical ways to structure datasets for clarity and efficient processing. We'll cover schemas, file formats, folder layouts, and basic metadata practices you should apply consistently. Every year, we generate far more digital content. Smartphone photos and videos, application logs, scanned contracts, and PDFs. Because most of this is unstructured or semi-structured, we must organize it now so it can be searched and used later. AI can automatically create captions for images and video and improve search by matching text queries to relevant visuals. For example, Google Photos uses AI to surface matching images, and Google Image Search can even synthesize new images when an existing one doesn't meet the user's need. AI can automate much of quantitative analysis. It writes code to produce charts, highlights unusual records, and builds predictive models like revenue forecasts. These tools speed insight but still require human review for assumptions, data quality, and interpretation. AI can extract structured fields from messy documents, so systems can organize and search them. Simple examples are credit cards, driver's licenses, receipts, tickets, and contact blocks in emails. Harder cases include contracts, reports, and charts. The intelligent data processing market is growing quickly. Forecast at $12.81 billion by 2030 with a 32.9% annual growth rate, which reflects strong enterprise demand. In this section, we'll explore how to automate recurring tasks and handoffs across tools. You'll learn the principles and practical steps to design reliable, maintainable workflows that save time and reduce errors. AI should take on repetitive chores so people can focus on higher value work. For end users, that means letting the system handle things like booking restaurants, requesting refunds, planning trips, and filling out forms. Simple tasks that add up to a lot of saved time. Enterprises can use AI to automate repetitive work like lead management, invoicing, reimbursements, customer requests, and data entry. A powerful further use is data synthesis. Models can generate labeled examples which humans review and correct, creating better training data in a feedback loop. We'll cover data synthesis techniques in Chapter 8. Many real-world tasks need access to external tools. Booking a restaurant might require a web search for the phone number, making a call, and adding the reservation to your calendar. AIs that can plan and orchestrate those steps are called agents, and they attract strong interest because they can greatly amplify personal productivity and economic value. Chapter 6 explores agents in detail. It's fun to imagine new AI products, but enthusiasm alone doesn't justify building them. Before you start, evaluate feasibility, the real user value, and potential risks. We'll walk through those considerations next. Doing this early saves time and prevents harmful or pointless projects. We'll introduce a practical framework for planning AI applications, focusing on how to find valuable use cases and assess their feasibility. By the end of this section, you'll know how to move from idea to a realistic, risk-aware plan. With AI's rapid progress, the fastest way to learn is by building real projects. If you want to learn and have fun, jump in and experiment. Hands-on work reveals capabilities and limits more quickly than theory alone, and many teams use this approach to upskill. If you're doing this professionally, take a step back and ask why you're building it and how you'll sustain it. Foundation models let you build impressive demos quickly, but turning a demo into a profitable product needs product, market fit, a clear business model, and reliable operations. In this section, we'll evaluate candidate use cases to determine which best align with our goals and constraints. I'll guide you through weighing benefits, costs, and risks so you can prioritize the most promising opportunities. Start by asking why you want to build the application. Often the decision is driven by specific risks to mitigate or opportunities to capture, business problems that AI can address. In the next slides, we'll look at examples of risks, ordered from high to low. Start by reading the problem carefully. Identify exactly what is being asked, list the givens and constraints, and note any relationships or formulas that might apply. If AI poses an existential threat to your core business, adopting AI must be a top priority or competitors will displace you. Gartner, 2023, found 7% of organizations cite business continuity as their reason for embracing AI, especially in document-heavy sectors like finance and insurance, and in creative fields such as advertising and web design. See the OpenAI study, GPTs are GPTs, Elandu et al., 2023, for industry exposure rankings. This first point introduces the central idea we'll develop. I'll explain the core concept, why it matters, and then show a concrete example to make it clear. If you ignore AI, you'll miss practical ways to cut costs and grow revenue. AI can reduce user acquisition spend with better ad copy, product descriptions, and visuals, increase retention through improved support and personalization, and speed up sales, internal communication, market research, and competitor tracking. This is the first item in our sequence. Here we'll introduce the main idea and set up what to prove or compute in the following steps. You may not yet know where AI fits in your business, but studying and experimenting now is safer than waiting until a disruption forces your hand. History, Kodak, Blockbuster, BlackBerry shows the cost of delay. If you can afford it, allocate time and resources, often via R&D at larger companies, to explore how AI could impact your products and processes. Once you've chosen a use case, decide whether you must build it yourself. If AI poses an existential threat or would give competitors a strategic advantage, in-source it for control. But if the goal is productivity or profit, buying or partnering can save time, cut costs, and often give better performance. Weigh control, risk, and cost. In this section, we'll map which tasks the AI handles and which require human judgment, oversight, or intervention. You'll learn where automation helps, where humans add value, and how responsibility is shared across the system. The role AI plays inside a product affects nearly every design decision. Architecture, data pipelines, UX, and privacy requirements all depend on how AI is used. Apple's guidance organizes common AI use patterns. Next, we'll focus on 3 points that matter most when defining development and requirements. Ask whether a feature or component is critical, required for the system's core function, or complementary, something that improves the experience but isn't strictly necessary. That distinction guides priorities. Make critical parts robust and well-tested, while planning complementary features for later iterations or lower-risk changes. If an app still functions without the AI feature, that AI is complementary. It adds value but isn't required. Face ID is an example of essential AI. Facial recognition is core, and the feature fails without it. By contrast, Gmail Smart Compose improves writing speed, but Gmail still works perfectly well without the AI. If AI is central to an application's purpose, its accuracy and reliability must be higher. People tolerate mistakes when AI is peripheral, but when AI drives outcomes, a failure can break workflows, cause harm, or destroy user trust. Reactive means you wait and respond after a problem appears. Proactive means you anticipate issues and act beforehand. Proactive approaches reduce surprises and often cost less in the long run, while reactive responses are important when events are unexpected or information is lacking. Reactive features wait for user action or request and then respond. For example, a chatbot replying to your message. Proactive features look for opportunities and act without an explicit prompt, like Google Maps showing traffic alerts when it detects congestion ahead. Reactive features are computed on demand in response to events, so they typically need to be fast to meet user expectations. Proactive features can often be pre-computed and surfaced opportunistically, which relaxes latency requirements. That said, proactive results sometimes need freshness, so low latency can still matter in certain cases. Because users didn't ask for these features, low-quality suggestions often feel intrusive or annoying. That means proactive predictions and generated content need higher accuracy and relevance before they're surfaced. Prioritize testing and careful filtering. Dynamic content changes while the program runs, driven by user input, timers, or external data. Static content is fixed at build time and served unchanged, which makes it simpler and faster to cache. Use static for performance and predictability. Use dynamic when content must update or respond to users. Dynamic features are updated continually using user feedback and live signals, so they adapt as people and usage change. Static features are updated only when the product is changed or upgraded. For example, Face ID must adapt over time to users' changing appearances, while Google Photos object detection is typically improved only with app/model updates. Dynamic personalization adapts per user. For example, each user might have their own model that's continually fine-tuned on their data or a memory feature that stores preferences. Static personalization uses a single shared model for a group of users, and those features only change when that shared model is updated. Decide whether the AI will support humans, take actions directly, or combine both approaches. For a customer support chatbot, that can mean draft suggested replies for agents to edit, automatically send responses without human review, or suggest replies, but auto-send only when confidence is high. Make the responsibilities, review gates, and safety limits explicit so everyone knows who decides what. This short paragraph restates the central idea in plain language and highlights a single practical takeaway. Focus on the intuition, what matters, why it works, and one concrete action or result to remember. The system presents several suggested responses that a human agent can reference, adapt, or send as is. This speeds up reply writing and helps keep responses consistent while the agent remains in control. Begin by stating the central idea in a single sentence. Follow with one brief supporting sentence that shows why it matters or gives a short, concrete example, and avoid extra jargon or repetition. The AI will answer straightforward queries by itself. If a request needs deeper judgment, context, or raises safety/legal concerns, the system routes it to a human reviewer to ensure accuracy and responsibility. When a proof feels messy, break it into three parts. State the definitions and assumptions. Prove one or two key lemmas. Then assemble those lemmas into the final argument. This keeps each step focused and makes it easier to check correctness and spot gaps. While models can generate replies automatically, many real-world systems use human review, content filters, or approval workflows before delivering answers. Models also make errors and depend on training data and system design, so they don't act like fully autonomous agents in most deployments. Human in the loop means people stay involved in an AI system's decisions. They review, correct, or approve outputs before final action. This hybrid approach helps catch mistakes, handle unusual cases, and provide accountability that pure automation can miss. Microsoft 2023 proposes treating product automation as a progression through three stages: crawl, walk, and run. Start with conservative, human-in-the-loop features, crawl, move to more autonomous assistance with human oversight, walk, and finally deploy high-confidence, largely autonomous capabilities, run. Each step increases capability and risk. Begin by reading the problem carefully to identify exactly what is being asked. Jot down the given data, constraints, and any implicit assumptions before you try to solve it. The crawl phase means the process cannot run on its own. People must set up, operate, or approve important steps. Expect manual work, regular oversight, and human decisions rather than full automation. This first point states the central idea we'll examine. Keep it in mind, it frames the examples and techniques that follow. Here, walk means the AI can initiate or respond in conversations and workflows with staff inside the organization. That includes asking clarifying questions, sending updates, or triggering actions, all subject to access controls and oversight. Begin by clearly stating what you want to achieve. A precise goal focuses your approach, guides which methods to use, and makes it possible to tell when you've succeeded. Here, run means moving from manual steps to increased automation, sometimes including AI that directly interacts with external users by sending messages, answering requests, or taking actions. That improves speed and scalability, but also introduces new safety, privacy, and oversight needs. Early on, use the AI to generate suggestions that human agents review and either accept or edit while you evaluate capability. If humans consistently accept AI outputs at a high rate, for example, 95% of suggested responses for simple requests, you can safely let customers interact directly with the AI for those cases. Now we'll examine how to build defensible AI products, the features, data strategies, and business design that create sustainable competitive advantage. I'll outline practical levers you can use to make your AI offering harder for competitors to replicate. If you sell AI applications as standalone products, defensibility is crucial. The low entry barrier that helped you build can also let competitors replicate your work quickly. Focus on durable moats, unique training data, proprietary models, deep integrations, network effects, regulatory or contractual locks, or operational scale that make your product costly or slow to copy. Building an app as a layer on a foundation model risks that model absorbing your functionality as it improves. For example, a PDF parsing app that assumes ChatGPT can't parse PDFs would lose its edge if the model later handles PDFs well. You retain value only by targeting different needs, e.g., using open source models for in-house hosting or other unique features. A common VC concern is that if a startup is essentially one useful feature, big platform owners like Google or Microsoft can re-implement it quickly inside their products. With existing distribution and engineering teams, they can assign a few engineers and ship a competing feature in weeks, which can wipe out the startup's advantage. This highlights the risk of relying on a lone feature without other defensibilities. Firms compete on three main axes in AI: technology, data, and distribution, the ability to bring a product to users. Because foundation models make core technology more similar across companies, data and user access become the decisive levers. Large companies tend to hold the distribution edge since they already control major channels to users. Big companies often start with more historical data, but that advantage isn't absolute. A startup that reaches users first and continuously gathers usage signals can improve iteratively and build a lasting moat. Because usage patterns reveal behaviors and product weaknesses that guide what data to collect and how to train models. Many well-known startups began as focus features that big companies could have added, but didn't. Think Calendly versus Google Calendar, MailChimp versus Gmail, or Photoroom versus Google Photos. By solving a single, important problem exceptionally well, a small product can grow into a company that outcompetes larger rivals. If you find an overlooked feature with real user value, that focused approach could be your path to scale. In this section, we'll set clear, realistic expectations for what this lesson will cover and what you should be able to do afterward. We'll outline the scope, any prerequisites, and how to measure your progress. Before building, decide how you'll measure success and focus on business impact rather than technical niceties. For a customer support chatbot, track metrics like response time, cost per ticket, resolution rate, customer satisfaction, CSAT, self-service rate, and any effect on retention or churn. Here we state the core idea concisely. Identify the main assumption, note its immediate implication, and spell out one concrete consequence. This short chain helps build a mental model before we move on to examples or formal details. Decide what share of incoming customer messages you want the bot to handle end-to-end versus handing off to a human. Balance customer experience, accuracy, and complexity. A common approach is to start conservatively, for example 30 to 50%, and increase the target as the bot proves reliable. This short line on screen shows the core idea. Use your voice to expand with examples, reasoning, and important nuances. Keeping the visible text brief helps viewers focus on the explanation without reading ahead. Pick enough recent messages to keep the conversation coherent while staying inside the model's context window and your cost/latency limits. A practical default is the most recent 8 to 20 messages, or roughly the last 2 to 3K tokens. Also offer user-adjustable setting so people can increase or decrease that range. Before you start solving, pause to list what is given, what must be found, and any constraints or units. Decide which formulas or theorems apply, and note any simplifying assumptions. For example, steady state, linear, negligible friction. Taking this small step first prevents common errors and saves time later. Chatbots usually give instantaneous answers for simple queries, seconds instead of the minutes or hours a human might take. For complex, judgment-heavy tasks, they speed up initial steps, research, drafts, routing, but often still need human follow-up. Overall improvement depends on task complexity and system latency. Put only the essential words on the screen and move details into your narration. Short, readable captions reduce cognitive load and let the viewer focus on the explanation you provide aloud. Estimate the time each task takes today and how much the chatbot reduces that time or eliminates the task entirely. Multiply the time saved per task by the task volume, daily or monthly, to get total hours saved. Finally, subtract review/oversight time and add maintenance/setup work to get a realistic net labor savings. Handling more messages is useful, but increased throughput alone doesn't mean users are happier. You should measure customer satisfaction and gather qualitative feedback. A simple ratings plus comments feedback system helps you spot problems and prioritize fixes. The user feedback section shows how to design that system in detail. Prevent shipping unfinished products by setting a usefulness threshold, a clear, measurable definition of how good the product must be to actually help customers. Express this with concrete metrics, for example, availability, accuracy, latency, adoption. Clear thresholds, stop premature releases, and align the team on readiness. Pause for a moment and reflect on the key idea we just covered, what it means, and how you might use it. When you're ready, we'll move on to examples that make the idea concrete. We evaluate chatbot answers across several dimensions rather than a single score. Important metrics include accuracy. Are facts correct? Relevance. Does the reply match user intent? Coherence and fluency. Clear, grammatical text. Factuality and hallucination rate. Safety and bias. Plus user-centered measures like satisfaction and task success. Operational metrics such as latency and consistency also matter. Display only the essential phrase or formula on screen, and speak the fuller explanation. This keeps the viewer focused on the key idea while your narration provides context, examples, and nuance. Latency is measured by TTFT, time to first token, TPOT, time per output token, and overall total latency. Each highlights a different part of the response pipeline. What's acceptable depends on your customer's expectations. For example, if humans currently respond in about an hour, any automated latency well below that is likely good enough. This block is empty and appears to be a placeholder. Either replace it with the intended paragraph text or remove the block. If the gap is deliberate, add a brief note explaining why it's blank. This metric measures the money spent each time the model handles one input, a single inference request. It captures compute, memory, and network charges and is often expressed as $/request or $per 1,000 requests, which helps with budgeting and model selection. This line marks a deliberate placeholder or omission in the material. Use it as a pause to insert your own example, note, or to skip content that isn't needed for your current purpose. Beyond accuracy, we evaluate interpretability, how understandable a model's decisions are, and fairness, whether performance is equitable across groups. These require different measures like feature importance, counterfactual explanations, and subgroup error rates, and can introduce trade-offs with raw accuracy. If you haven't chosen metrics yet, that's perfectly fine. The rest of the book introduces many common metrics, explains how they're calculated, and shows when each one is useful so you can decide as you go. In this section, we'll break the project into concrete milestones, set target dates, and assign responsibilities so progress becomes measurable and predictable. After you set measurable goals, make a plan that depends on where you start. Test existing models to see how much of the goal they already achieve. The better they are out of the box, the less custom work you'll need. For example, if you need 60% ticket automation and an off-the-shelf model already handles 30%, your remaining effort is much smaller than if it handled 0%. Evaluation can reveal that reaching a useful product requires more time, money, or effort than the expected return. When that happens, you should adjust your goals, for example, by narrowing scope, deprioritizing the project, or deciding not to pursue it further. Foundation models let you assemble impressive demos quickly, so an initial prototype can seem deceptively easy. Turning that demo into a reliable, scalable product. Handling edge cases, integrations, latency, safety, and ongoing operations often takes months or years. Both Ultra Chat, Ding It All, and LinkedIn observed a common pattern. Getting a product to a usable 80% is fast, but pushing from there to near perfection is slow. They achieved most of a user-facing experience in 1 month, then spent 4 more months chasing the last gains, largely fixing product kinks and reducing hallucinations, incorrect or fabricated outputs. So each additional percent felt increasingly costly and discouraging. In this section, we'll cover routine upkeep, common troubleshooting steps, and best practices to keep the system reliable. I'll point out what to monitor, how to schedule maintenance, and when to escalate problems. Hitting your product goals is only the beginning. You also need a plan for how the product will evolve and be maintained. In AI, this matters more because models, tooling, and best practices change rapidly. Building on foundation models today means committing to ongoing monitoring, updates, and adaptation. Many model limitations are being addressed. Context windows are expanding and raw outputs are improving. At the same time, inference, the process of computing outputs from inputs, has become markedly faster and cheaper. Figure 1:11 visualizes how inference costs dropped while MMLU benchmark performance rose between 2022 and 2024. Look at how the numbered points are distributed across the axis. Note any clusters, gaps, or obvious outliers. Pay attention to the numbering sequence. It can show progression or ordering, and check whether the points suggest a clear trend or a more scattered relationship. This figure illustrates how the computational cost of AI reasoning has fallen sharply over time. It's from Katrina Nguyen, 2024, and we'll refer to it to discuss impacts on model scaling and deployment choices. Every new technology choice requires a continuous cost-benefit check. The option that looks best today can become the worst tomorrow. For example, building a model in-house may seem cheaper until providers drop prices, or tailoring systems to a third party can fail if that vendor goes out of business. As vendors align on common APIs, technically switching from one model to another becomes easier. But models differ in behavior and performance, so teams must adjust prompts, workflows, and data, and without good versioning and evaluation infrastructure, those changes often cause headaches. Many countries treat AI as a national security issue, so key resources, compute, talent, and data are heavily regulated. Large rules like GDPR required costly compliance, and recent executive actions can instantly restrict who may buy or sell compute hardware. If a GPU vendor is suddenly blocked from selling to your country, your training plans and operations can be halted overnight. Regulations for AI and intellectual property are still changing. So using a model trained on other people's data creates legal uncertainty about who owns the product's IP. That uncertainty can be fatal for products whose value depends on proprietary content, which is why many IP-heavy firms, like game studios, avoid such AI. When designing a system, factor in ownership risk and plan for legal changes. After you commit to building an AI product, you must assemble an engineering stack that turns models into reliable features. This includes data collection and labeling, model development and training, compute and storage, serving infrastructure and APIs, plus monitoring, observability, and governance. We'll unpack each layer next. In this section, we'll outline the AI engineering stack, the layered components and practices that turn models into reliable production systems. We'll walk through each layer, its responsibilities, and the common tools you'll see in real projects. AI engineering's rapid growth has produced a lot of hype and FOMO. New tools and models appear daily, and it's easy to feel overwhelmed. Instead of trying to chase every trend, we'll focus on the fundamental building blocks that stay useful even as the landscape shifts. AI engineering grew directly out of ML engineering. When companies start using foundation models, their existing ML teams usually lead the work. So many organizations treat AI engineering as equivalent to ML engineering, even though AI engineering can expand responsibilities beyond traditional ML tasks. This is a screenshot of a computer display. Focus first on the overall layout, where the main panels, menus, or toolbars sit, and which area contains the primary content. When you analyze such images, identify the dominant content region, then scan for headings, navigation elements, and any dense text blocks that likely carry the key information. This figure illustrates how many companies list AI engineering and ML engineering under a single job umbrella. We'll examine this example to understand why titles overlap and what that implies for hiring and role expectations. Many companies create distinct job descriptions for AI engineering instead of bundling those tasks into general software roles. These separate descriptions emphasize responsibilities like model development, production deployment, and maintaining data and inference pipelines. AI engineering and machine learning engineering share many skills and responsibilities, even when companies label them differently. ML engineers can add AI engineering to expand career options, but there are also AI engineers who entered the field without prior ML experience. We'll break the AI application stack into layers: data, models, orchestration/runtime, and user-facing components, and look at what each layer requires. Doing this highlights how AI engineering shifts focus from model training alone to runtime reliability, prompt and chain design, integration, and operational concerns. This screenshot shows the application's main window. Focus first on the central content area where the primary information is displayed. Notice the toolbar along the top, any side panels or lists on the left or right, and the status or message area near the bottom. These elements tell you where to find controls and contextual information. Use these visual cues to orient yourself before diving into details or interacting with the interface. This figure shows that some companies list dedicated AI engineering roles instead of general software titles. These LinkedIn job headlines from December 17th 2023 illustrate how hiring language is shifting toward specialized AI positions. In this section, we'll break the AI stack into three clear layers to see how models, systems, and applications fit together. I'll outline each layer and explain its role so you can map real-world tools onto this framework. Any AI product sits on three stacked concerns: the app you build and its UX, the models that provide intelligence, and the infrastructure that runs and scales them. Teams usually start at the app layer and only move down into model work or infra when they need custom behavior, performance, or control. Application development is the end-to-end process of designing, building, testing, deploying, and maintaining software. It brings together requirements, programming, quality assurance, and operations so teams can deliver reliable features that users depend on. With models widely available, most of the recent activity is building applications that sit on top of them. Their work focuses on giving models clear prompts and the right context, then rigorously evaluating their outputs. Equally important is designing interfaces that make those models reliable and useful for real users. Model development is the process of turning data and a problem statement into a working predictive system. It covers defining objectives, preparing and engineering features, selecting and training algorithms, validating and iterating on performance, and making sure the model is robust and ready to deploy. This layer provides the practical frameworks and tools you use to build and optimize models, covering modeling, training, fine-tuning, and inference optimization. It also includes dataset engineering because data shapes model behavior, and it enforces rigorous evaluation to verify that models meet their goals. Infrastructure means the physical and organizational systems that make services possible: roads, power and water networks, data centers, and communication links. Think of it as the foundation that lets businesses, governments, and communities operate reliably and at scale. The infrastructure layer sits at the bottom of the stack and provides the tooling to serve models, manage data, and compute resources and monitor system health. This layer is what makes deployments reliable and scalable, and it gives teams the observability and controls needed to operate models in production. Figure 114 maps typical responsibilities onto each of the three layers, so you can see which concerns belong where. Use this visual mapping to decide where to implement features, enforce boundaries, and reduce coupling between parts of the system. This diagram shows a typical software development process from requirements through delivery. Notice the major stages, the handoffs between roles, and the feedback loops that enable iteration. Pay attention to where testing and deployment sit in the flow. Those are common places to improve cycle time and quality. We'll walk through the three layers of the AI engineering stack and see how they fit together. Use this figure as a roadmap to understand each layer's responsibilities and typical tools. I searched GitHub in March 2024 for AI-related repositories with at least 500 stars, using GitHub as a practical proxy for ecosystem activity. The search included both application repositories and model repositories and returned 920 projects in total. Figure 1:15 shows the cumulative number of repositories in each category month by month to illustrate how the landscape evolved with foundation models. This chart displays counts of people. First, check the axes and labels to confirm whether it's by category or over time. Pay attention to the overall shape, where the counts peak, any sharp rises or drops, and whether the distribution looks concentrated or spread out. This figure displays how the total number of repositories in each category accumulates over time. We'll read it to compare adoption rates across categories and spot periods of rapid growth or slowdown. The data shows a large jump in AI tooling in 2023, triggered by breakthroughs like Stable Diffusion and ChatGPT. The biggest increases were in applications and application development, while the infrastructure layer grew more modestly. That smaller infrastructure growth makes sense because core needs, resource management, serving, and monitoring, remain largely unchanged even as models and apps evolve. Despite the excitement around foundation models, the core engineering goals are unchanged. Solve business problems, map business metrics to ML metrics, and run systematic experiments. With foundation models, you experiment over models, prompts, retrieval methods, and sampling settings, while still optimizing cost and latency and maintaining a feedback loop to improve from production data. Much of what ML engineers learned over the last decade remains relevant, so existing best practices make it easier to start building AI applications. On top of those enduring principles, AI engineering introduces new patterns and tools. We'll explore those innovations in this book. We'll compare AI engineering and ML engineering, what each role focuses on, where they overlap, and how their responsibilities differ in practice. This will set the stage for concrete examples of design, deployment, and long-term maintenance choices. The fundamental rules for deploying reliable systems still hold, but practical practices have shifted with AI. Teams must adapt platforms for model serving, latency, and data privacy needs, while developers should learn ML ops, prompt engineering, and improved observability to stay competitive. In this lesson, we'll cover three major shifts when building applications with foundation models versus classic ML engineering. Broadly, foundation models bring large pre-trained capabilities used via prompts and APIs, change how we iterate and debug at runtime, and shift work toward model orchestration, safety, and integration instead of training bespoke models from scratch. We'll work through problem one step by step. First, I'll restate the goal, list what's given and what's unknown, and then outline a short plan before solving. In the past, you typically trained a new model for each application. Foundation models change that. You start from a large pre-trained model someone else built, and your job becomes adapting it via prompts, fine-tuning, or retrieval, rather than training from scratch. That shift changes the skills and tools teams need. This marks the first step of the process. Clearly state the goal for this step and show the concrete action or result the viewer should take away. Modern AI models are much larger and far more compute-hungry than traditional ML models, which increases latency and operating cost. That creates strong pressure to optimize both training and inference, and it often forces teams to scale up GPU capacity and hire engineers who know how to manage large compute clusters. This marks the first item or step. Use this moment to state the goal, record what is given, and decide what you must find or prove before proceeding. When models produce open-ended outputs, they can be applied to many kinds of tasks because the output isn't limited to a fixed label set. That flexibility is valuable, but makes evaluation a much bigger problem. Simple accuracy metrics often fail, so we rely on sampling, human judgments, and specialized benchmarks to measure real quality. AI engineering is more about adapting and evaluating existing models than developing new ones. Model adaptation techniques fall into two broad categories. Those that update model weights, for example, fine-tuning or training small adapters, and those that don't, for example, prompting, prompt engineering, or retrieval-augmented methods. Knowing which category you need guides trade-offs in cost, complexity, and performance. Prompt-based techniques adapt a model by giving it instructions and context instead of changing its weights. They're easy to start with, require less labeled data, and let you experiment across many models quickly, which often uncovers good, practical solutions. However, prompts can be insufficient for very complex tasks or applications that need consistently high performance. Fine-tuning means changing a model's weights so the model itself is adapted, not just the inputs. It typically requires more data and engineering than prompt-based approaches, but can substantially improve quality, latency, and cost. And it's necessary when you need the model to learn new tasks it never saw during pre-training. Let's zoom into the application development and model development layers to see what's different now that AI engineering is involved. We'll start from the ML engineer's perspective, outline the main development processes, and flag where workflows and responsibilities shift. Topics we'll revisit throughout the book. In this section, we'll outline the steps used to build and refine our predictive models, from data preparation through evaluation. I'll explain key design choices, training procedures, and how we measure performance. Model development is the part of the stack people usually picture when they think of ML engineering. It covers three core responsibilities: designing and training models, building and curating datasets, and optimizing inference for production. Evaluation is also required, but we'll discuss that in the next section. Now we'll move into how the model is constructed and trained. This section explains model architecture, the loss we optimize, and the training loop used to fit parameters. Modeling and training means designing a model's architecture, fitting that model to data, and then fine-tuning it for a target task. Tools like TensorFlow, PyTorch, and Hugging Face transformers provide the building blocks, training routines, and utilities you need for each stage. Building ML models requires specialist knowledge in 3 areas. You need to know algorithm families, for example, clustering, logistic regression, decision trees, collaborative filtering, and neural network architectures, feed-forward, recurrent, convolutional, transformer. And you must understand how models learn, concepts like gradient descent, loss functions, and regularization, to train, tune, and diagnose models effectively. Foundation models let many people build AI applications without learning the internals of machine learning. I've met successful builders who never bothered with gradient descent. Still, understanding ML expands your toolbox and makes it much easier to diagnose and fix problems when a model doesn't behave as expected. In this section, we'll define and contrast 4 terms you often see in model development: training, pre-training, fine-tuning, and post-training. I'll explain when each step is used, how their data and objectives differ, and why those differences matter. Training specifically means updating model weights by optimizing a loss using data. By contrast, quantization changes the numeric representation of weights to save space or speed up inference, but does not adjust them to improve performance. So we don't call it training. People often say simply training, but that umbrella term actually covers several distinct stages. Pre-training is the model's broad initial learning. Fine-tuning adapts it to a specific task, and post-training covers later adjustments like safety tuning or calibration. Pre-training is the model's initial phase where it learns broad language patterns from very large, mostly unlabeled corpora using self-supervised objectives like next token or mass token prediction. This builds general representations and fluency that later fine-tuning adapts to specific tasks. Pre-training means training a model from scratch with randomly initialized weights. For LLMs, this commonly uses text completion objectives. It is by far the most expensive and time-consuming phase. InstructGPT used about 98% of total compute and data, so errors during pre-training are costly and the skill is highly specialized. Fine-tuning means taking a pre-trained model and continuing training it on labeled, task-specific data so it performs well on that task. We usually use a smaller learning rate and fewer epochs than during pre-training to avoid destroying useful representations. This approach is efficient and effective with limited data, but watch for overfitting or catastrophic forgetting and validate carefully. Fine-tuning means we resume training from an existing model. Its weights come from prior training instead of being initialized randomly. Because the model already contains useful knowledge from pre-training, fine-tuning usually requires far less data and compute than training a model from scratch. After training, we evaluate the model on held-out data, calibrate its outputs, and apply any needed fine-tuning or pruning. Then we deploy the model, monitor performance and data drift in production, and iterate using new labeled examples or updated objectives. Technically, these terms describe the same step: additional training after pre-training. People often use post-training when a model developer refines a base model, for example, OpenAI improving instruction following, and fine-tuning when an application developer adapts a model to a specific task. A model can be post-trained by its vendor and later fine-tuned by you. Pre-training and post-training lie on a continuum. They share pipelines, infrastructure, and many of the same tools. The main distinction is purpose. Pre-training builds broad, general capabilities from huge data sets, while post-training adapts or refines those capabilities for particular tasks or constraints. We'll examine their differences in detail in chapters 2 and 7. People often use trained when they really mean they taught a model via prompts. For example, feeding childhood journal entries in a chat GPT to mimic your younger self is prompt engineering. It uses the model's context window, not weight updates. True training or fine-tuning involves changing the model's parameters by continuing gradient-based training on new data. This section introduces dataset engineering, the practices that make data reliable, reusable, and fit for training ML models. We'll cover labeling strategies, pre-processing, validation, and iteration workflows you'll use to build high-quality datasets. Dataset engineering means assembling and preparing the data we feed into models, selecting sources, creating or augmenting examples, and adding labels. It directly affects model accuracy, generalization, and bias, so careful curation and annotation are essential. Close-ended tasks let a model choose from a fixed set of answers. For example, spam versus not spam. Foundation models handle open-ended outputs like essays or creative responses, which are much harder to annotate reliably. Because annotating open-ended queries is subjective and time-consuming, data annotation becomes a far bigger engineering challenge for AI systems. Traditional ML typically works with structured, tabular datasets, while foundation models consume unstructured inputs like raw text, images, or audio. As a result, AI engineering focuses less on feature tables and more on dataset operations, deduplicating, tokenizing, retrieving relevant context, and enforcing quality and safety. For example, removing sensitive or toxic content. We'll dive deeper into dataset engineering in Chapter 8. As base models become commoditized, dataset quality and size are often what give teams an edge. The amount of data you need depends on the adapter. Training from scratch typically demands the most data, fine-tuning requires less, and prompt engineering requires the least. That's why dataset engineering is increasingly important for real differentiation. No matter how much data a model used, knowing what that data looked like is essential when you examine a model. The training set tells you where the model is likely to do well, where it may fail, and what kinds of biases or gaps to expect. So domain expertise is very helpful for interpreting those signals. In this section, we'll cover practical techniques to speed up model inference and reduce resource use. We'll look at quantization, pruning, batching, and runtime level optimizations, and when to apply each. Inference optimization means making model predictions faster and cheaper. It's a core ML engineering goal because users value lower latency and companies save on compute costs. As foundation models scale, inference cost and latency grow, so optimization is increasingly critical. Many large models generate tokens one after another, so latency grows with output length. For example, at 10 milliseconds per token, a 100 token reply takes about 1 second, but users expect 100 ms, which is why inference optimization is now a major industry and research focus. This table summarizes how different model development categories change in importance as teams adopt AI engineering practices. In production-focused AI work, operational areas, data pipelines, deployment, monitoring, and robust evaluation become more central, while exploratory research and one-off modeling projects decline in relative emphasis. Foundation models change what teams spend their time on. Training models from scratch becomes less common, so deep ML expertise is helpful but often not strictly required, though some experts disagree. Dataset engineering shifts away from handcrafted features toward deduplication, tokenization, retrieval of relevant context, and data quality work, and optimizing inference performance grows even more important for production systems. Chapters 7 through 9 introduce practical ways to speed up and shrink models for real-world use. Quantization reduces numeric precision to save memory and compute. Distillation transfers knowledge to a smaller model, and parallelism splits work across hardware. Together, these techniques lower latency and cost for production inference. In this section, we'll cover the essentials of application development, common workflows, key architecture decisions, and deployment considerations. I'll guide you through what matters at each stage so you can design, build, and ship reliable software. In traditional ML, teams compete by building proprietary models, so model quality itself is the advantage. When many teams use the same foundation model, that shared base removes model as differentiator. Now uniqueness comes from the application, data, fine-tuning, prompt design, UX, and system integration. The application development layer handles three practical responsibilities. Evaluation measures model outputs against your goals and metrics. Prompt engineering crafts the inputs to steer the model. And the AI interface connects the model to your app, managing formatting, retries, and safety checks. Now, we turn to evaluation, how we measure model performance and choose the right metrics for a task. I'll outline common metrics, typical pitfalls, and how to interpret results so you can compare models reliably. Evaluation isn't a one-time check. It's needed throughout model adaptation. Use it to pick models, benchmark progress, decide deployment readiness, and to detect problems or improvement opportunities once a system runs in production. Evaluation is both more important and more difficult for foundation models because their outputs are open-ended and their capabilities are broader. In closed tasks like fraud detection, you can compare outputs to a known ground truth. But for chatbots, there are many valid responses, so you can't build an exhaustive list of correct answers. Having many adaptation techniques makes model comparison fragile. Google evaluated Gemini on the MMLU benchmark using a prompt engineering method called COT at 32, where Gemini saw 32 examples while ChatGPT was shown only 5. When both models were evaluated with the same 5-shot setup, ChatGPT actually performed better, so matched evaluation conditions are essential. This table shows how MMLU accuracy changes not just with model, but with how you prompt it. Chain of thought, COT, prompting, and more reasoning steps can boost performance. For example, Gemini Ultra scores 90% with COT at 32 versus 83.7% in a 5-shot setting. Smaller or older models like GPT 3.5 and Llama 2 remain considerably lower under these comparisons. In this section, we'll learn how to craft prompts and organize context so a model gives clearer, more reliable results. You'll see practical techniques for framing tasks, supplying relevant background, and structuring prompts for predictable behavior. Prompt engineering means shaping model behavior by changing the input prompt, not the model weights. Small but smart prompt changes can yield large improvements. For example, Gemini Ultra's MMLU score jumped from 83.7% to 90.04% after a different prompting technique. This shows prompt design can strongly affect evaluation and real-world performance. Well-crafted prompts plus the right contextual information and tools let a model perform tasks in the exact format you need. For complex tasks with long context, add a memory management system so the model can track history and maintain coherence. See Chapter 5 for prompt techniques and Chapter 6 for context and retrieval strategies. In this section, we'll examine the AI interface, the components and interaction patterns that let users communicate with models. We'll focus on input methods, feedback mechanisms, and practical design constraints. An AI interface is the way end users access and use an AI capability inside an application. Before foundation models, only organizations with enough resources could build these AI features, and they were usually embedded into existing products. For example, fraud detection in Stripe, Venmo, and PayPal, or recommender systems in Netflix, TikTok, and Spotify. Foundation models let anyone build AI apps that you can either ship as standalone products or embed inside other software. Standalone examples include ChatGPT and Perplexity. Embedded examples are GitHub Copilot as a VS Code plugin, Grammarly as a browser extension, and Midjourney, which also offers a Discord integration. Real-world AI needs usable interfaces, tools that let you build standalone AI products or easily add AI features to existing software. In the next slides, we'll examine the common interface types that are gaining popularity and why each one matters. This short paragraph states the central idea and why it matters for what follows. Focus on the single takeaway sentence that captures the concept and on any terms introduced here that we will use later. These are applications packaged to run independently across platforms, in browsers as web apps, as native desktop programs, or as mobile apps. Standalone builds bundle the runtime and resources so users can install or run them without extra setup, which simplifies distribution. Show the central point briefly on screen, then expand verbally. Focus on the core intuition and one practical implication so learners remember the takeaway. These are browser extensions that let you query AI models without leaving the page. Common features include selecting text to get summaries, explanations, translations, or drafted replies that use the current page context for faster, in-place assistance. Keep on-screen text short and focused. A single clear phrase or sentence. Reserve details, examples, and clarifications for the spoken narration so viewers can read the board quickly and listen for nuance. Many chatbots run directly inside messaging platforms such as Slack, Discord, WeChat, and WhatsApp. They let users and teams trigger actions, receive notifications, or hold conversational workflows without leaving the chat app. This brief note highlights the main point. Concentrate on the single core concept and set aside irrelevant details. Carry this focus into the next example so the reasoning stays clear. Many products expose APIs that let developers build plugins and add-ons to embed AI directly into the app experience. The same APIs can be called by AI agents to perform actions and interact with external systems. This is covered in Chapter 6. Chat is the most familiar way people interact with AI, but it's not the only one. Some systems are voice-based, like assistants on phones or speakers, while others are embodied inside augmented or virtual reality, changing how users perceive and control the system. These different modes affect design choices and user expectations. Conversation interfaces make it much easier for users to give feedback in plain language, so you get richer and more frequent responses. The challenge is extracting reliable, structured signals from that open-ended text. User feedback design and solutions are discussed in Chapter 10. Table 1.6 gives a compact view of which app development categories become more or less important as AI engineering takes center stage. Use it to guide where to reallocate effort, for example, toward data, model integration, and operationalization, and away from areas that matter less in AI-first apps. This compares how three app development categories change when you move from traditional ML to foundation models. Foundation models make the AI interface much more important and make prompt engineering a new, essential skill, whereas prompt work doesn't apply to classic ML. Evaluation stays important in both workflows, but becomes even more critical with foundation models because their outputs are broader and harder to verify. In this section, we'll compare AI engineering and full-stack engineering, focusing on their typical responsibilities, workflows, and skill sets. I'll highlight where the roles overlap and where they require different approaches and tooling. As interfaces and application development become central, AI engineering is shifting closer to full-stack work. Front-end skills now matter alongside model expertise. Tooling is expanding beyond Python to JavaScript APIs, for example, LangChain.js, Transformers.js, OpenAI's Node library, and Vercel's AI SDK, though Python remains widely used. Many AI engineers still come from traditional ML backgrounds, but an increasing number are coming from web or full-stack roles. Those engineers can prototype and ship working demos quickly, build a UI, deploy it, and collect user feedback. That rapid loop lets teams validate ideas and improve models or UX much faster. Traditionally, ML projects begin with collecting data and training models, with the product coming last. Today, because strong AI models are available off the shelf, you can prototype the product first and only spend on custom data and model training once the product proves valuable. This reverses upfront cost and risk and is illustrated in Figure 1.16. Notice how the arrows fill the frame and converge toward a common direction. That creates a strong sense of motion and focus. Also observe the contrast and surface texture on the arrows. These visual cues guide the eye and establish visual hierarchy. This figure shows how modern AI engineering rewards teams that can iterate quickly. We'll use it to highlight the key feedback loops and tools that make fast experimentation decisive in model development. Traditionally, model development and product design were separate. ML engineers focused on training and deployment, while product teams drove features. With foundation models, model behavior directly shapes user experience. So AI or ML engineers become active partners in product decisions and iterative design. In this summary, we'll revisit the main goals, methods, and key results from the lesson. I'll highlight the practical takeaways and suggest the next steps for applying what you learned. This chapter had two aims. First, to show how the availability of foundation models gave rise to AI engineering as a distinct discipline, and second, to present a high-level process for building applications on top of those models. It's an overview chapter, so it only touches many concepts briefly. Each will be explored in detail in later chapters. AI has changed fast. Simple language models scaled into large language models by using self-supervised training, which unlocked much greater capability. Those LLMs then incorporated images, audio, and other modalities to become foundation models that serve many tasks. The rise of these broad, reusable models is what gave practical shape to today's field of AI engineering. Foundation models have unlocked a wide range of practical applications, which is why AI engineering has grown so quickly. We've seen many consumer and enterprise patterns reach production, but this is still the early phase. Countless innovations remain to be built. Before you start coding, pause and ask whether the product should exist at all. Evaluate business value, technical feasibility, data availability and privacy, ongoing maintenance costs, and safety or regulatory risks. These factors decide if building is the right move. AI engineering grew out of ML engineering. So many core practices carry over. At the same time, AI engineering introduces new problems and solutions, and the final chapter section explains how the AI engineering stack differs from traditional ML engineering. The AI community brings enormous collective energy, creativity, and engineering talent. That steady flow of new techniques, discoveries, and impressive engineering work is exciting, but often overwhelms any single person trying to stay fully up to date. AI is excellent at collecting and summarizing many new developments, which makes staying current easier. Still, tools only take us so far. When a field is overwhelming, a clear framework is what lets us navigate, prioritize, and apply the information. This book offers that kind of organizing framework. From here, we'll unpack the framework step by step, beginning with the core building block of AI engineering, foundation models. These models power many of today's impressive applications, so we'll study how they work and how to use them effectively. I use the label traditional ML to mean any machine learning methods that came before the era of foundation models, from classical supervised and unsupervised techniques to earlier deep learning systems. Using this shorthand keeps our comparisons concise when we later discuss how foundation models differ. Tokenizers don't always map one visible character to one token. For some scripts, or for characters composed from multiple Unicode code points, a single displayed character can be split into several tokens, which raises the token count and can affect cost and input limits. These models predict each token using only earlier tokens, so they're called causal. Predictions cannot peek at future words. This left-to-right, causal factorization is what enables autoregressive text generation. BERT is a bidirectional masked language model, not an autoregressive generator, so it doesn't produce text left to right by default. You can repurpose it for generation by repeatedly masking and filling tokens, or using Gibbs sampling and other hacks. But those methods are indirect, slower, and typically less natural than using an autoregressive model. Labeling costs depend on three main factors: how hard the labeling task is, how large your dataset is, and which service you use. Volume matters a lot. Per image prices typically fall as you label more data. For example, in September 2024, Amazon SageMaker Ground Truth charged about 8 cents per image for under 50,000 images, but around 2 cents per image when labeling more than 1 million. Knowing when to stop matters. Once your point is clear, further talking often distracts or dilutes the message. Pausing or ending on time respects listeners and keeps communication effective. We used to treat weights and biases as two distinct kinds of parameters in models. These days, many people casually say weights to mean all learnable parameters, including biases, so always check the author's or code's terminology when it matters. This sounds counterintuitive at first. A more powerful model might seem like it should learn from fewer examples. In reality, higher capacity models can represent much more complex patterns. So to use that capacity and avoid overfitting, we need more diverse data. We're trying to maximize performance, not just reproduce what a smaller model can do. To put AI funding in perspective, U.S. public elementary and secondary schools spend about $900 billion a year, roughly 9 times what the U.S. invests in AI. That implies AI investment is on the order of $100 billion, so education spending is much larger than current AI funding. A snapshot from September 16th, 2024. Teresa Naifer that.com lists 16,814 AI tools mapped to 14,688 distinct tasks and 4,803 job-related tools. This highlights how rapidly AI has diversified into many niche tasks and roles, making discovery and curation increasingly important. Keep this scale in mind as we talk about specialization and how to find the right tool. One of my favorite parts of writing this book is exploring the many AI applications people build. I maintain a curated list of open-source AI projects so readers can browse real examples. The list is refreshed every 12 hours to keep it current. Enterprises typically allocate a large share of their budgets to advertising and marketing, so applying automation there can produce substantial savings. A Wall Street Journal analysis found companies spend about 11% of their budget on marketing on average, though that share varies by industry. I used AI during the book's writing to generate ideas. For example, to suggest what might happen next or how a character could react. I'm still evaluating which parts of fiction writing can be reliably automated and which require human creativity and judgment. I predict growing skepticism will make people avoid anonymous or algorithmic content and stick to sources they already know. That shift would concentrate attention on verified creators and familiar brands, changing how information spreads online. Big device makers often move more slowly because they set higher bars for accuracy, safety, and legal compliance before releasing new capabilities. Voice assistants also add engineering complexity, low-latency streaming, reliable wake word and microphone handling, and heavy testing across accents and environments. So integrating generative models takes longer than deploying a text chat feature. Quick disclosure, I serve as an advisor to Convai. I'll note any parts of the material where that relationship might be relevant to interpretations or recommendations. I have over 40,000 photos and videos in Google Photos. Without AI-driven indexing and recognition, manually finding a specific shot would be impractical. AI lets me search by people, places, objects, or moments instead. When a graph is overloaded, ask an AI to break it down for you. It can identify the main trend, point out outliers, and clarify axes and labels so the chart becomes easy to interpret. Very small teams usually can't spare a person for exploratory research or scouting. That means discovery must be lightweight and embedded in delivery. Founders or engineers combine observation with building, and choices are prioritized by immediate product impact. Early on, people joked that a lot of generative AI startups were basically thin interfaces around models like OpenAI or Claude. That captures 2 points: how rapidly products could be built on powerful APIs, and how hard it is to achieve lasting differentiation beyond a core model. While researching this book, I heard the term from almost every AI startup. It describes a feedback loop. User activity generates data. That data improves the model. The better model improves the product, and that attracts more users, a self-reinforcing cycle central to many AI businesses. Quick transparency. I hold an investment in Photorum. When I discuss the company, keep that potential conflict of interest in mind, and I'll point out where my ownership might affect my perspective. This highlights a common gap. Teams that are comfortable with small GPU clusters often lack the tooling and practices for thousands of GPUs. At that scale, you face different challenges: orchestration, fault tolerance, cost control, and large-scale debugging, which require distinct skills and operational processes. Companies often offer highly competitive compensation packages to attract top talent. These typically mix base salary, performance bonuses, stock or equity grants, and generous benefits like health coverage and paid leave. Calling procedures, pre-training, and post-training works, but it's unimaginative, and that's typical in AI. We routinely use vague labels like large in large language model, and publish punchy titles such as X is all you need, which can obscure precise meaning rather than clarify it. These three libraries are popular ways to turn machine learning models into interactive web apps without writing a full front end. Streamlit and Gradio focus on rapid prototyping and simple interfaces, while Plotly Dash gives more control for dashboard-style applications. Anton Bakaj is saying AI engineering builds on the same foundations as software engineering, design, testing, deployment, but with AI models inserted into the stack. Those models add new responsibilities like data management, model versioning, monitoring for drift, and inference performance.